Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good morning. I hope all of you are doing well. For today, we are going to continue the lecture on shaft power cycle. There are a few sub-topics that we need to cover for today. Right, we are still in the topic of shaft power cycles, and we will look into the methods for accounting component losses. So we have gone through the last 2 weeks on looking into the stagnation properties, compressor and turbine efficiencies, asentropic efficiency, polytropic efficiency, and pressure losses. So for today, we will focus on the heat exchanger effectiveness, mechanical losses, variation of specific heat, fuel-air ratio, combustion efficiency and cycle efficiency, and finally bleeds flow. So that will wrap up our subtopic of 2.2 methods of accounting for component losses. In terms of the learning outcomes, so at the end of the session, you should be able to calculate the heat exchanger effectiveness, meaning that later in our example, okay, you will be able to calculate the effectiveness of the heat exchanger and then explain the mechanical losses in an air breathing engine, right? And then later on, you should be able to describe the effect of variation of specific heats on the cycle performance. It depends on the gas that we use for the in the gas turbine engine. And then analyze the effect of fuel to air ratio on combustion efficiency as well as the cycle efficiency. And finally, you should also be able to explain the importance of bleeds flow and the application in the gas turbine engine. So those are, among others, the important learning outcomes that you should be able to obtain by the end of this particular session. Right, let us look into heat exchanger effectiveness. If you look here, the heat exchanger effectiveness, where heat exchanger for gas turbine can take many forms, including counter flow, right? We have the normal counter flow and cross flow, or name as recuperators, where the hot and cold stream exchange heat through a separating wall. So these particular figures showing the heat exchanger flow configurations. We have the concurrent flow, we have counter current flow, right, where the flow is in the opposite direction, okay, and the cross flow, where we cool the heat exchanger this way, and the cross as well as counter flow, which is hybrid heat exchanger flow configuration. Or we can also have a regenerators, where the streams are brought cyclically into contact with a matrix which alternately absorbs and reject heats. So this is coming from paper from Astolfi, 2017, schematic representation of a regenerator fin tube bank. So we have fins, okay, where we have the, let me just quickly get my pen, right? So that so these are the fins, okay, and these are the tubes. These are the arrangement of a regenerator fin tube bank, typical, and its disposition and turbine outlet. Okay, right. If we look here, figure 2.13, the pressure losses, using the notation in figure 2.13, the fundamental process is that the turbine exhaust gases will reject heat at the rate of M, or mass flow time the specific heat capacity, at 4 to 6, okay, at 4 to 6 here, right, with the temperature difference of TO4 to TO6, while the compressor will deliver, that is at the turbine stage, while the compressor deliver air, we receive heat at the rate of MC, or mass flow rate at the compressor times the specific heat at constant pressure at from 2 to 5, okay, with a temperature difference between the TO5 to TO2. All right. If we look carefully on the conservation of energy, we assume the mass flow rate at the turbine and at the compressor, okay, are equal. Okay, this is equation 2.21, right? And we have this expression, okay, at the turbine as well as the compressor. Okay, so let me just use my pen again, right? So this is okay, I'm very sorry. This is at the turbine, right? And this is at the compressor. Okay. So, but both TO5 and TO6 are unknown. And a second equation is required. So, whenever we want to solve the problem, we have to to use another equation, which is provided by the equation expressing the efficiency of the heat exchanger. So now the maximum possible value, okay, maximum possible value of TO5, right? So TO5, in other words, which is here, okay, is when the cold air attains the temperature of the incoming hot gases. TO4. TO4 is the temperature at coming out from the combustion chamber, right? And one possible measure of the performance is the ratio of the actual energy received by the cold air to the maximum possible value. So this is the expression of the performance, the ratio of the actual energy received. So the mean specific heat of air will not be different over the two temperature ranges, and it is usual to define the efficiency in terms of temperature alone and to call it the thermal ratio or the thermal ratio effectiveness of the heat exchanger. So we have the component of the temperature, right? All the temperature component, right? We took temperature component TO5, TO2, TO4, and TO2, and then we call this as the thermal ratio effectiveness. Thermal ratio. So when a value of the effectiveness is specified, equation 2.22 will enable the temperature at the inlet to the combustion chamber TO5 to be determined. So equation 2.21 then yields TO6 if required. Okay, note that so the mean specific heat at constant pressure CP4 to 6 and CP to 5 are not the same, right? So it is different and cannot be cancelled because the value are not the same. One is at the turbine, the other one is at the compressor. Okay, so this is at the turbine, and CP value for the compressor. So and we know that for the former, okay, turbine is exhaust gas, and for the compressor is only air. Okay, the product. So the larger the volume of the heat exchanger, the higher the effectiveness, but it is limited to few items. And the first one is the heat transfer surface area. Okay, and it also limited to the turbine exit and inlet temperature fixed by the materials used, right? So it depends on the TIT, turbine inlet temperature, and TET, turbine exit temperature. And the thermal stresses during startup, okay, hence not suitable for frequent starts are required. Okay, that's what we can say on the heat exchanger effectiveness. Later when we look at the example, you will see that it makes sense in terms of the item that we already discussed. Now, we look into the mechanical losses. In a gas turbine, the power necessary to drive the compressor is transmitted directly from the turbine without any intermediate gearing, right? So that we already know in our early chapters that we already discussed about this. And any loss that occurs is therefore due to bearing friction as well as the windage. So this loss is very small, okay? And it is normal to assume that amount to about 1% of the power necessary to drive the compressor. So it is not that significant, but it need to be considered if you want to increase the performance of the gas turbine engine. So if the transmission efficiency is denoted by zeta m, okay, we call it as the mechanical zeta m. So we have it here, okay, the M stand for mechanical, okay, and we have the work output required to drive the compressor given by this expression. Hence, we shall take zeta m, okay, the efficiency, transmission efficiency to be around 0.99%, just to take account into the 1% loss. So earlier we mentioned about 1% losses. Okay, so we just take it out and we use the value of 0.99 for the transmission efficiency. So any power used to drive ancillary components such as fuel and oil pumps can often be accounted for simply by subtracting it from the net output of the unit. Right? Let us look into the variation of specific heat. Okay, depends on because specific heat earlier we mentioned about specific heat at the turbine, specific heat capacity at the compressor. It is different. So what are the effect of the variation of the specific heats? So the properties of the specific heat capacity at constant pressure and the specific heat ratio gamma, okay, play an important part in the estimation of the cycle performance, and it is necessary to take account of variations in values due to changing conditions through the cycle. Right? In general, for real gases over normal working range of pressure and temperature, Cp is a function of the temperature alone. So it is only the function of the temperature. So the same is true for the specific heat ratio, gamma, because it is related to Cp, right? So this is a relationship by equation 2.23, okay, where R is the molar universal gas constant and the capital M is the molecular weight, right? So the variation of Cp, specific heat capacity at constant pressure, and gamma is shown clearly in this figure 2.14 by the curves marked 0 air fuel ratio. Okay, this is the specific heat capacity. Okay, and then we also have the gamma. So if we look here, the variation of the specific heat capacity against the gamma in terms of the temperature different, right? So the specific heat capacity itself, right, increases, right, when the temperature increases, right? But okay, let me just read it again. So the specific heat capacity, we look one by one. Specific heat capacity, right? Cp, right? And then the gamma variation, right? From if we look at the specific heat capacity from 1 point roughly about nearly to 1 to 1.4, 1.4 over here. So if you have a temperature of 1600 degrees Kelvin, right, you have a value of Cp of 1.2, compared if you have a temperature of 600 degrees Kelvin, you have a value of nearly to 1 for the specific heat capacity. Whereas for the specific heat ratio, gamma, okay, if we have the same condition, right? The same condition for the 1000 degrees, 1600 degrees Kelvin, right? So you have roughly around, let's say we pick one point there, and you will have the specific heat ratio of nearly 1.25. Okay, so it depends on what gases that you use, and is it air or is it a exhaust product. Okay, only the left hand portion is of interest, because even with a pressure ratio as high of 35, right, the compressor delivery temperature will not be more than 800 Kelvin. So basically this part of the graph is much more important, right? Okay, this part of the graph is much more important for because the compressor delivery temperature will be not be more than 800 degrees Kelvin. Right. So the same figure 214 shows that the CP increases while the gamma decreases with increase of fuel to air ratio, and it is both the CP and the gamma are closely related by equation 2.23, with this molar air value to be 0.287 kilojoule per kilogram Kelvin, right? And the calculation of the product analysis is very lengthy, and we are not going to go through the calculation of the product analysis, okay, when dissociations is taken into consideration, since CP and gamma becomes a function of the pressure and temperature. So to make simplified, in our calculation later on, we are going to just to use the values given in the question. So dissociation become significant when the temperature is above 1500 Kelvin, right? So it is very significant because it will depend on the pressure and the temperature. So for preliminary design in the compression and expansion processes, we will use this constant value for example, like for air, we are going to use a value of specific heat capacity at constant pressure of 1.005. Okay, for combustion gases, right? So we are going to use a value of 1.148. Okay, while the gamma for air we will use 1.40, while for the combustion gases you are going to use 1.33. So these two values, these four values for the CP as well as for the gamma, you must be very careful whenever you treat the CP, for example, for CP for turbine, okay, for turbine, right, you must use the value for the gas, okay, while for the compressor, you then use the value for the air. Okay, so those are the two situation. You will see this in the example that we are going to go through later on. Okay, when to use CPA for 1.005, when to use CPG 1.148. Okay, if you use the wrong values, you will get the wrong answer. Okay, the next one is fuel air ratio. Okay, another item that we need to use many times in our example, the combustion efficiency as well as the cycle efficiency, right? So the performance of real cycle can be expressed in terms of the specific fuel consumption and the fuel mass flow per unit net power output. That is what specific fuel consumption all about. So since the process is adiabatic, means that no heat transfer, the energy equation is simply being given by this expression, right? Where M dot, okay, the mass flow is the product I per unit mass of air and HI is its enthalpy. Right. Making use of the enthalpy of reaction at a reference temperature of 25 degrees Celsius, the difference of enthalpy from 2 to 5, the compressor to the exit of the turbine, the equation can be expanded in to become this long expression. All right. So let me explain where CPG, okay, the mean specific heat of the products over the temperature range. So CPG, remember when you want to use the value of the CPG, okay, so you will have to use the correct one. And then the change of enthalpy should be the reaction per unit mass of fuel with the H2O, okay, in the products in the vapor phase because TO3 is high and above the dew point. So this is the figure, okay, figure 2.15, which is the combustion temperature rise versus fuel air ratio, okay. So it depends when the temperature, this is the axis of the axis of the y-axis basically is the y-axis, okay. So this is let's say we can see y-axis is the combustion temperature rise assuming complete combustion, right? And then down underneath here is the fuel ratio, right? Where you have the lower units at 0.04 up till 0.14, and we continue on top of here is 0.016 and so on, right? So basically the graph itself, it is actually being divided into two, where we put the higher temperature, okay, the higher temperature values, this part, okay, on top. Actually it is a continuation, and this part is actually continue from there. So to make life easy, because it is going to be very big, so we combine it into one graph. So and over here also we have the combustion temperature. Okay, sorry, the inlet air temperature. These are another values that very important. You will be given the inlet air temperature, and you have to calculate the combustion temperature rise. So it depends on the situation. So later when we go through the example, you will use this particular figure again and again and again. Okay, now we look into the data in figure 215, which have been calculated on the assumption that the fuel is completely burned. So we assume what the fuel is completely burned. So this is one of the assumption that we are going to make, okay, where the fuel is completely burned. And the most convenient method of allowing for combustion loss is by introducing a combustion efficiency defined by zeta B. So we have gone through zeta M just now, okay. We have zeta T, we have zeta C, now we have zeta B, okay, the combustion efficiency, which is given by the theoretical value of the fuel air ratio for given temperature different and the actual fuel air ratio for a given temperature different, right? So once the fuel air ratio is known, right, by using figure 2.15 just now, the fuel consumption, okay, of the mass flow of the fuel is simply the fuel air ratio times the mass flow. Okay, the M is the air mass flow, and the specific fuel consumption can be found from SFC equal to F over WN. Okay, so let me just correct this. Okay, this one basically the MF. Okay. Since the fuel consumption is normally measured in kilogram per hour, while the WN, the work, okay, is in kilowatt per kilogram per second of airflow, this specific fuel consumption is written as kilogram per kilowatt hour, okay, and will be given by the following equation, right? This is the equation. In the gas turbine, it is not possible to utilize the latent heat of H2O vapor in the products. Okay, we assume it is insignificant, and the convention of using the net calorific value, thus the cycle efficiency may be defined as this expression, right? With the units used here, the equivalent numerical equation will become this expression, right? Or using the above numerical equation for specific fuel consumption, right? So you can rewrite it where Q net is sensibly equal in magnitude but opposite in sign to the enthalpy of reaction H25, referred to earlier, and the value of 43,100 kilojoule per kilogram will be used. So in most of our example, we will be using the Q net value given as 43,100 kilojoule per kilogram, right? And the final subtopic for the methods of accounting for component losses is talking on the bleed flows. And in terms of the bleed flows, the turbine inlet temperatures are limited by metallurgical considerations. So we know that many modern engines make use of air-cooled blades to permit elevated temperatures, and it is possible to operate with uncooled blades up to 1350 Kelvin to 1400. Okay, then it can be assumed that the mass flow remains constant throughout. So if you want to use more higher temperature, you need to have the cool blades, right? As I said just now, at higher temperature, more beyond 1400 degrees Kelvin, it is necessary to extract air to cool both the stator and the rotor blades, because it cannot be withstand by the existing materials of the stator and the rotor blades. So the required bleeds may amount of 15% or more. Okay, it depends on the type of the engine, from the compressor delivery flow, and must be properly accounted for in accurate calculation. So you have to take into account this 15% m dot coming into the mainstream of the air. And then the overall air cooling system for such an engine is complex, right? But the methods of dealing with bleeds can be illustrated using a simplified example as shown here in figure 216. Okay, this is a typical stator. Okay, right. Let me just get a pen. Probably having blue color, right? Okay, so this is stator. This is rotor blade. Okay, where the air coming from the compressor will be used as the cooling air. This is a cool air coming out. So this is the cool air goes out from the turbine blades, rotor blades, and even from the stator. So there are cold air coming into the stator that will protect the stator blades. So this is what we call it as the film cooling. A single stage turbine with cooling of both the stator and rotor blades will be considered, okay, where beta D, beta S, and beta R denote the bleeds for cooling the disc stator and rotor respectively. So in other words, we need to know how much amount of air being bled into the stator, how much air needed to be used to protect the rotors. So it's not that easy task. So note that the bleed beta D, okay, acts to prevent the flow of hot gases down the face of the turbine disc, but it does pass through the rotor. So the stator bleeds also passes through the rotor, and both contribute to the power developed. The rotor bleed, however, does not contribute to the work output, and the reduction in mass flow results in an increase in both temperature drop and pressure ratio for the specified power. So whenever you are dealing with the turbine cooling, we also have impingement cooling, transpiration cooling. There's so many other types of internal cooling as external cooling being used to protect the turbine blades. If the airflow at the compressor delivery is given as MA, then the flow available to the rotor MR is given by this expression. So the fuel flow is found from the fuel-air ratio required for the given combustion temperature rise and combustion inlet temperature. And the air available for the combustion is given as this notation. And the final slide is here, where this figure 219 showing cooling air distribution. Okay, so let me just read through this. The distribution of air cooling in a hypothetical multi-stage turbine. So we have the multi-stage turbine. This is a turbine. Okay, this is the nozzle guide vane, the first stage of turbine with that the combustion chamber output will meet or experience, and then we have the other turbines, which gives some idea of the complexity and the need to understand fully the location of various bleeds. So basically, the gas turbine engine designer, especially the internal cooling engineers, they have to calculate the amount of high pressure cooling air that comes from the high pressure compressor, okay, being supplied through the complex mechanism of the engine, okay, and how much going to be bled, okay, in terms of the sizes of the cooling holes, the location of the cooling holes, and the respective temperature and pressure. They also need to know in terms of the mass flow rate, the velocity, the impingement velocity, the cooling effectiveness, the heat transfer coefficient need to be mapped in order for them to ensure a proper cooling for the blades. So the bleed flows is very important as part of the to ensure the performance of a gas turbine to be at the maximum. Okay, that's for the second subtopic for the shaft power cycle, right? Going to stop share there.